and today's video is on equilibrium calculations.
So having developed the idea of the equilibrium quotient expression Q, and that equilibrium constant is the value of Q at equilibrium at a temperature, we find ourselves on the verge of this big leap to equilibrium calculations. So the first thing we'd like to be able to do is to be able to predict some shifts in equilibrium systems. We'd like to observe a system and determine which direction, to the left or to the right, the system will shift to reach equilibrium. So in order to do that, remember, observe and then determine which direction the system is going to go. In order to do that, we'll compare this reaction quotient Q to KQ. Now remember, Q, that quotient, is the concentration of products divided by reactants. So let's imagine this scenario here, I'm just making it up now, that KQ for the system is 20 at some temperature, and then we observe and calculate a reaction quotient of 5. So it's pretty clear that reaction is not at equilibrium. If so, Q would equal KQ, but they don't. And it's pretty clear that the products of reactants, that ratio Q is too low. And because it's too low, clearly we need more products and less reactants to increase the ratio. We'll say that this reaction will shift to the right to reach equilibrium. So the idea there is if Q is greater than KQ, of course that would suggest a shift to the left. So let's summarize that then. And we'll say if we know what the KQ is for a system and Q is larger than it, the reaction will shift left to meet equilibrium. So if Q larger, will shift to the left. And if Q is smaller than KQ, the system will shift to the right. This is worth remembering. Now let's see an example. Here's the nitrogen monoxide and oxygen gas forming nitrogen dioxide here. This has a KQ of 49 at some temperature. So in our example, we'll have just 2 moles of nitrogen monoxide, and we'll get 0.2 moles of oxygen gas and 0.40 moles of nitrogen dioxide, and we'll put all these in a 2-liter container. So here's the question. Well, is the system at equilibrium? Did we get very lucky? Is it at equilibrium? And if not, which direction will it proceed to go towards equilibrium? Will it shift left or shift right? So here's the way to solve the problem. Just write the equilibrium expression, make sure you get all the correct exponents in there, and then we'll put in the values. Now remember, these values are concentrations. So we'll put them in here as concentrations. Notice what they are as numbers of moles divided in each case by that volume of 2 liters. So let's make sure we got this right. It's 0.4 in 2 liters, 2 in 2 liters, and 0.2 all in 2 liters. Yes, that's all working. Make sure the exponents are correct. Compute this value, it's 0.40. Well, it's a lot smaller than KQ, so this system should shift to the right. Okay, so that's the idea of the reaction quotient. Too small, smaller than KQ, shift right. Too big, shift left. And it's a great example. So here it is once again. If Q is less, we'll shift to the right. If Q is greater than KQ, shift left. So have a look at the next 2 videos and stay tuned for our next lesson, lesson 10, Equilibrium Calculations, part 2.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.